Are we truly alone in the universe? Tonight, we're going to explore one of the most unsettling discoveries in modern astronomy, that our solar system might be far rarer than we ever imagined. You've probably heard that there are billions of stars in our galaxy, each potentially hosting planets of their own. It seems natural to assume that systems like ours should be common throughout the cosmos. But here's what most people don't realize. The specific combination of factors that makes Earth habitable is so astronomically unlikely that it challenges everything we thought we knew about life in the universe. By the end of this journey, you're going to understand exactly why our cosmic address might be a 1 in a billion lottery ticket, and why that discovery is both wonderful and deeply troubling. Before we dive in, if you enjoy these kinds of explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. When you look up at the night sky, you see thousands of stars sparkling above you. Each point of light represents a distant sun, potentially surrounded by planets of their own. The Milky Way contains between 200 billion and 400 billion stars scattered across its disk. With so many stars, it seems natural to assume that planetary systems like ours are common throughout the cosmos. But let me share something that might surprise you. That assumption, it might be completely wrong. The Earth orbits what astronomers call a G-type star, our Sun, with a surface temperature of 10,400 degrees Fahrenheit. Our Sun is 4.6 billion years old and finds itself approximately at the middle of its useful life. Think about that for a moment. Our star converts 600 million tons of hydrogen into helium every single second through nuclear fusion. This reaction releases energy equivalent to 400 trillion watts of continuous power. Picture this enormous furnace burning in space, 93 million miles away from where you're sitting right now. Every second, it consumes material equivalent to the mass of 600 Empire State Buildings, converting it into pure energy through a process so violent that it would vaporize any known material instantly. Yet this cosmic inferno burns with such perfect stability that its energy output varies by less than 1/10 of 1% over decades. Now here's where things get interesting. The Sun represents only 1 in every 10 stars in the galaxy, with enough stability to support life. Let that sink in for a moment. 9 out of 10 stars in our galaxy are fundamentally unsuitable for harboring complex life forms. The smaller stars, called red dwarfs, make up 70% of all stars but present intense flaring activity. These stellar eruptions, sudden explosions of electromagnetic radiation, can sterilize nearby planets in a matter of decades. Picture this. You're living on a planet orbiting a red dwarf star. One day, without warning, your star unleashes a burst of radiation so intense it strips away your planet's protective atmosphere and boils away its oceans. In just a few decades, what was once a thriving world becomes a barren, lifeless rock. Imagine if our Sun suddenly became 10,000 times brighter for several hours, repeatedly, without warning. The radiation would penetrate deep into Earth's atmosphere, destroying the ozone layer that protects us from harmful ultraviolet light. The surface of our planet would become as hostile to life as the interior of a microwave oven. This is the reality for planets orbiting red dwarf stars. On the other end of the spectrum, stars larger than our Sun burn their fuel far too quickly, lasting only millions of years. That might sound like a long time to you, but in cosmic terms, it's barely a blink. If the entire history of the universe were compressed into a single year, these massive stars would live for less than an hour before exploding as supernovas. Evolution needs billions of years to work its patient magic, transforming simple molecules into the complex chemistry of life and eventually into beings capable of looking up at the stars and wondering about their place in the universe. It took nearly 4 billion years for life on Earth to progress from the first simple cells to the complexity of human civilization. Massive stars simply don't provide enough time for this intricate process to unfold. Only G-type and K-type stars provide the billions of years of stable brightness necessary for biological evolution. This immediately reduces the number of suitable candidates by 90%, leaving us with only about 40 billion stars in the Milky Way. 40 billion sounds like a lot, doesn't it? But we're just getting started with our cosmic lottery. Our sun resides in what astronomers poetically call the galactic suburbs, approximately 26,000 light-years from the center of the Milky Way. Being in this suburban location offers crucial protection against the intense radiation of the central galactic core. To put this distance in perspective, if you could travel at the speed of light, 671 million miles per hour, it would take you 26,000 years to reach the galactic center. The galactic center harbors a supermassive black hole, an object so dense that not even light can escape its gravitational pull. Containing 4 million times the mass of our sun, let me help you visualize what a supermassive black hole means. Imagine taking 4 million suns, each one nearly 900,000 miles across, and compressing all that mass into a region smaller than the orbit of Mercury. The gravitational field becomes so intense that it warps space and time itself, creating a region from which nothing, absolutely nothing, can return once it crosses the boundary. Star systems close to the galactic center experience 10,000 times more cosmic radiation than we do here in the suburbs. Think about that. 10,000 times more radiation would sterilize any planet's surface, making it impossible for complex life to develop or survive. It would be like living inside a nuclear reactor that never shuts off. But our favorable location goes beyond just distance from the galactic center. Our orbital position around the galaxy keeps us away from the dense spiral arms for extended periods. These spiral arms contain regions of active star formation, where supernovas, explosions of dying massive stars, occur with frightening frequency. A single nearby supernova, within about 30 light-years of Earth, could destroy our planet's ozone layer in a matter of weeks. When a massive star explodes as a supernova, it releases more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. The explosion creates a shock wave that travels at speeds of 6,000 miles per second, carrying deadly gamma radiation across interstellar distances. If such an explosion occurred within our cosmic neighborhood, the radiation would strip away Earth's protective ozone layer, allowing lethal ultraviolet light to sterilize the surface. The sun's orbit through the galaxy has a period of approximately 225 million years, called a galactic year. During this period, we cross through the spiral arms only occasionally, minimizing our exposure to catastrophic events. It's like living in a cosmic safe zone, carefully threading our way between the galaxy's most dangerous neighborhoods. This combination of location and orbital movement is rare, occurring in less than 5% of all stars. But there's another factor that makes our situation even more extraordinary. The sun orbits the galaxy in almost perfect synchronization with the speed of the spiral arms themselves. This synchronization, when the orbital speed of the star matches the spiral pattern, is like walking on a treadmill at exactly the same speed that it's moving. Stars with this characteristic remain outside the dense zones of the spiral arms for much longer periods. Most stars that traverse spiral arms frequently encounter giant molecular clouds with masses equivalent to millions of suns. These encounters can disturb something called the Oort cloud, a reservoir of comets located 50,000 astronomical units from our sun. An astronomical unit is the average distance between Earth and the Sun, equivalent to approximately 93 million miles. The Oort cloud extends to a distance of over 4,600,000,000,000 miles from the Sun. So far that if you could drive there at highway speeds, the journey would take more than 6 million years. Perturbations in the Oort cloud send comets hurtling toward the inner solar system, dramatically increasing the frequency of catastrophic impacts on planets like Earth. These icy visitors from the outer reaches of our solar system can be miles across and travel at speeds of up to 100,000 miles per hour when they reach the inner planets. Geological evidence shows that the rate of comet impacts varies cyclically with periods of 30 million years. These cycles coincide precisely with the Sun's passages through the spiral arms, confirming the danger of these dense regions. It's as if the galaxy has a heartbeat, and every beat brings increased risk to any life that might be developing on worlds within the spiral arms. Therefore, before we even consider planets, only 1 in 200 stars has the correct type, location, and trajectory for potentially supporting complex life. We've eliminated 99.5% of all stars in the galaxy simply by requiring basic stellar stability and a safe galactic neighborhood. But Johannes Kepler observed in 1609 that planets orbit the Sun in ellipses, not perfect circles. An ellipse is an oval shape with 2 focal points, like a circle that's been flattened on the sides. The orbital eccentricity measures how much an orbit deviates from a perfect circle, ranging from 0 to 1. Earth possesses an orbital eccentricity of only 0.017, meaning its orbit is nearly perfectly circular. To put this in perspective, if you drew Earth's orbit on a piece of paper, you wouldn't be able to tell the difference between it and a perfect circle without extremely precise measuring instruments. This near-perfect circularity is extraordinarily rare among planets. Circular orbits maintain constant distance from the star, ensuring relatively stable surface temperature throughout the year. Think about what this means for life on our planet. As Earth travels around the Sun, it stays within a narrow band of distance, never straying more than about 3 million miles closer or farther from our star. This consistency prevents dramatic temperature swings that would make complex life impossible. The habitable zone, the region where liquid water can exist on a planet's surface, varies depending on the type of star. For our Sun, this zone extends from approximately 88 million miles to 127 million miles from the star. Earth orbits at exactly 93 million miles, placing it perfectly within this ideal range for liquid water. Liquid water is fundamental because all known biochemical reactions depend on it as the universal solvent. Every process that occurs inside your body right now, from the firing of neurons in your brain to the beating of your heart, relies on water molecules to transport nutrients, remove waste, and facilitate chemical reactions. Without liquid water, life as we know it simply cannot exist. But here's where the precision becomes almost unbelievable. If Earth orbited just 5% closer to the Sun, a mere 4.5 million miles nearer, temperatures would trigger a runaway greenhouse effect. This runaway greenhouse effect occurs when water vapor accumulates in the atmosphere, trapping heat until it evaporates all the oceans. The planet becomes a superheated steam world, permanently uninhabitable. Venus, orbiting at 67 million miles from the Sun, suffered exactly this fate and now has a surface temperature of 864 degrees Fahrenheit. That's hot enough to melt lead, zinc, and tin. The atmospheric pressure on Venus is 92 times greater than Earth's, equivalent to being crushed under 3,000 feet of ocean water. What was once potentially a world with liquid water became a hellish furnace that would vaporize any spacecraft that tried to land on its surface. On the other side of the habitable zone, if Earth orbited 15% farther from the Sun, about 14 million miles more distant, water would freeze permanently, creating what scientists call a snowball effect. The snowball effect happens when ice reflects sunlight back to space, cooling the planet even more in a vicious cycle. Once this process begins, it's nearly impossible to reverse. Mars, orbiting at 141 million miles from the Sun, partially experienced this phenomenon and lost its dense atmosphere. Mars today is a frozen desert where the average temperature is minus 80 degrees Fahrenheit. Any liquid water on its surface would instantly boil away into the thin atmosphere or freeze solid, depending on the season and time of day. Data from the Kepler Space Telescope indicates that only 0.4 to 0.6 systems per Sun-like star have a rocky planet in the habitable zone. A rocky planet means a body composed primarily of silicates and metals, like Earth, Mars, and Venus, rather than a ball of gas like Jupiter or Saturn. This requirement eliminates the vast majority of discovered exoplanets, which are either gas giants or small worlds orbiting far too close or far too distant from their stars. This reduces the chances to approximately 1 in 250 stars harboring potentially habitable planets. But having a planet in the habitable zone doesn't guarantee conditions suitable for complex life. The chemical composition of the star itself, called metallicity, matters enormously. Metallicity refers to the abundance of elements heavier than hydrogen and helium in a star. Stars with very low metallicity don't provide enough heavy elements to form substantial rocky planets. Our Sun has a metallicity near 0.02, meaning that 2% of its mass consists of heavier elements. This might sound tiny, but it's crucial for creating rocky planets with iron cores and silicate mantles. First-generation stars formed shortly after the Big Bang contained virtually no metals. The Big Bang, the initial expansion of the universe 13.8 billion years ago, produced only hydrogen, helium, and traces of lithium. These primordial elements alone cannot create the complex chemistry necessary for rocky planets or life. Only after generations of stars exploded as supernovas did heavy elements spread throughout space. Carbon, nitrogen, oxygen, iron, and other elements essential for life are forged in the nuclear furnaces of stellar cores. When these massive stars reach the end of their lives, they explode with such violence that they scatter these precious elements across vast regions of space, seeding future generations of stars and planets. Our Sun is a third-generation star, formed from material enriched by at least 2 previous generations of stellar death and rebirth. This chemical inheritance was necessary to create Earth with its mineral-rich crust. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of these elements were created in the nuclear furnaces of ancient stars that died billions of years before our solar system even existed. Beyond stellar chemistry, the architecture of our entire solar system plays a fundamental role in Earth's habitability. Jupiter orbits at approximately 484 million miles from the Sun, with a mass equivalent to 318 times that of Earth. This gas giant exerts dominant gravitational influence over the entire inner solar system. Jupiter functions as a cosmic vacuum cleaner, capturing or deflecting asteroids and comets that would otherwise hurtle toward Earth. Picture Jupiter as an enormous gravitational shield, using its immense mass to alter the trajectories of potentially dangerous objects. Computer simulations show that without Jupiter's protective presence, the impact rate on Earth would be 1,000 times higher. With dramatically increased impacts, mass extinctions would occur every million years instead of every 100 million years. Life would barely have time to recover from one catastrophic bombardment before the next wave of destruction arrived. Complex organisms requiring millions of years to evolve would never have the opportunity to develop. Think about what this means for the history of life on Earth. The dinosaurs ruled our planet for 165 million years before an asteroid impact ended their reign. Without Jupiter's protection, similar impacts would have occurred every few million years, preventing any species from achieving long-term dominance and evolutionary sophistication. However, Jupiter must be at precisely the right distance. Too close, and it would destroy the inner planets. Most planetary systems observed by astronomers contain what are called hot Jupiters, gas giants orbiting extremely close to their stars. These misplaced giants migrate inward during the formation of their planetary systems, scattering or destroying any rocky planets that might have formed closer to the star. Hot Jupiters complete their orbits in just a few days, heated to temperatures exceeding 1,800 degrees Fahrenheit. They represent failed solar systems where gravitational interactions sent the giant planets careening inward, obliterating any chance for Earth-like worlds to develop in the habitable zone. The precise positioning of Jupiter in our solar system required an extraordinary sequence of events during the formation of our planetary system 4.6 billion years ago. Jupiter had to form at exactly the right time, after enough solid material accumulated to build its core, but before the gas disk around the young sun dissipated completely. This timing had to be perfect within a window of perhaps just a few 100,000 years, but Jupiter needed help to maintain its beneficial orbit. The gravitational influence of Saturn, with 95 times Earth's mass, played a crucial role in preventing Jupiter from migrating inward. These two giant planets entered into what astronomers call orbital resonance, when their orbital periods maintain simple numerical ratios that create gravitational stability. This resonance locked both giants in their current positions, preserving the inner solar system for rocky planets like Earth. Without this delicate gravitational dance between Jupiter and Saturn, our planet would never have existed, and you wouldn't be here to contemplate the extraordinary series of cosmic accidents that made your existence possible. However, Jupiter needs to be at the right distance. Too close, and it would destroy the inner planets. Most planetary systems observed by astronomers contain what are called hot Jupiters, gas giants orbiting extremely close to their stars. A hot Jupiter is a gas giant with an orbit of only 3 to 10 days, heated to temperatures exceeding 1,800 degrees Fahrenheit. These planets migrate inward during the formation of their planetary systems, scattering or destroying any rocky planets that might have formed in the inner regions. Imagine Jupiter suddenly appearing in Mercury's orbit, its immense gravitational field wreaking havoc on everything else in the solar system. Earth would either be flung out into the cold depths of space or pulled inward to incinerate in the sun's fires. Evidence from the Kepler Space Telescope indicates that approximately 1% of systems with gas giants have their Jupiter in the proper orbit. Think about that statistic for a moment. 99 out of every 100 planetary systems with gas giants have them in the wrong place, either too close to the star, destroying any chance for habitable worlds, or so far out that they provide no protection at all. Our Jupiter didn't migrate significantly because it probably formed after the protoplanetary disk. The cloud of gas and dust around the young sun began to dissipate. The timing had to be absolutely perfect. If Jupiter had formed too early, when the disk was still dense with gas, gravitational interactions would have dragged it inexorably toward the sun. If it had formed too late, there wouldn't have been enough material left to build such a massive planet. This delicate timing was combined with the gravitational influence of Saturn, which possesses 95 times Earth's mass. Saturn and Jupiter entered into orbital resonance, a condition where their orbital periods maintain simple numerical ratios, during the formation of our solar system. This resonance stabilized their orbits and prevented catastrophic migration toward the inner solar system. Picture two dancers moving in perfect synchronization, each one's movements keeping the other in balance. That's what happened with Jupiter and Saturn. Their gravitational dance locked them into stable orbits that preserved the inner solar system for rocky planets like Earth. This cosmic choreography had to unfold with precision that defies imagination. Combining all stellar and planetary factors we've discussed so far, less than 1 in 10,000 systems present this favorable configuration. But there's another critical element that makes Earth truly exceptional among all known planets in the universe. The Moon orbits Earth at an average distance of 239,000 miles, completing one orbit every 27.3 days. With a diameter of 2,160 miles, the Moon possesses more than 1/4 of Earth's diameter. This proportion is extraordinary. No other rocky planet in our solar system possesses such a relatively large moon. Mars has 2 tiny moons with diameters of only 14 miles and 7.5 miles, essentially captured asteroids. These misshapen chunks of rock are so small that an astronaut could literally walk around their perimeter in a single day. They provide no meaningful influence on Mars whatsoever. The mass ratio between Moon and Earth is 1:81, much greater than any other rocky planet-moon system in our solar system. To put this in perspective, if Earth were a basketball, the Moon would be a tennis ball orbiting about 24 feet away. No other planet in our solar system has anything remotely comparable to this arrangement. The Moon didn't form alongside Earth, nor was it captured gravitationally afterward. Evidence from lunar rocks collected by the Apollo missions between 1969 and 1972 reveals a completely different origin story. Oxygen isotopes, variants of atoms with different numbers of neutrons, in the Moon and Earth are practically identical. This isotopic similarity indicates that both bodies share common source material. If the Moon had formed elsewhere and been captured by Earth's gravity, its chemical composition would be distinctly different. If it had condensed from the same disk of material as Earth, the isotopic ratios would show subtle but detectable differences. Instead, the evidence points to a much more dramatic origin. The giant impact hypothesis proposes that 4.5 billion years ago, a protoplanet collided with the proto-Earth. This protoplanet, which scientists have named Theia after the Greek Titaness who gave birth to the moon goddess Selene, was approximately the size of Mars with a diameter of about 4,200 miles. Theia collided with Earth at an oblique angle, not head-on, at a speed of approximately 34,000 miles per hour. The impact released energy equivalent to 100 million trillion atomic bombs detonating simultaneously. To help you visualize this unimaginable violence, imagine every nuclear weapon ever built by humanity exploding at once, then multiply that destruction by 10 million. The collision vaporized most of the mantles of both bodies and ejected material into orbit around Earth. The mantle, the layer of rock between a planet's core and crust, contains the majority of mass in rocky planets. This superheated rock, vaporized at temperatures reaching 7,200 degrees Fahrenheit, remained in orbit around the devastated Earth. Within 100 years after the impact, this orbital debris began to clump together under its own gravity. The process of accretion, when particles gradually unite to form larger bodies, took approximately 1,000 years. During this time, Earth existed in a hellish state with a glowing ring of molten rock debris surrounding it, like a planetary version of Saturn's rings made of liquid stone. The resulting moon initially orbited at only about 15,500 miles from Earth, 16 times closer than today. At this distance, the moon would have appeared 16 times larger in Earth's sky. A massive, glowing orb dominating the heavens and creating tides hundreds of times more powerful than anything we experience today. Tidal forces, the differential gravitational pulls between the near and far sides of objects, gradually push the moon away from Earth. Currently, the moon recedes from Earth at a rate of 1.5 inches per year, a measurement confirmed by laser reflectors left on the lunar surface by Apollo astronauts. The probability of such an impact occurring requires extremely specific and improbable conditions. The impacting protoplanet must have a mass between 10 and 15% of the target planet's mass. Masses much smaller don't eject enough material to form a substantial moon, while larger masses would completely destroy the target planet, obliterating any chance for life to develop. The impact angle must be between 30 and 60 degrees relative to vertical. Head-on impacts destroy both bodies completely, reducing them to clouds of vaporized rock that never reassemble into planets. Glancing impacts that are too shallow result in the impactor bouncing off or passing by without sufficient material transfer to create a large moon. The impact velocity must fall within an incredibly narrow range, between 27,000 and 45,000 miles per hour. Speeds much faster would vaporize both objects entirely, while slower impacts wouldn't generate enough energy to melt and eject the necessary amount of material into stable orbit. The timing had to be perfect within the history of solar system formation. Too early, and the impact would have occurred when both objects were still largely molten from their initial formation, preventing the precise material transfer needed. Too late, and both planets would have developed thick atmospheres and crusts that would complicate the collision dynamics. Computer simulations indicate that only 1 to 3% of collisions between protoplanets produce large, stable moons. Even when all the mass, angle, and velocity requirements are met, the chaotic nature of such violent impacts means that most result in either no moon formation or the creation of multiple small moons that eventually crash back into the planet. Front-on impacts destroy both bodies, while glancing impacts result in separation without fusion. The relative velocity must be between 27,000 and 45,000 miles per hour, neither too fast nor too slow. Higher velocities would completely vaporize both bodies, while lower speeds wouldn't generate sufficient energy to create the precise conditions needed for moon formation. Think about the incredible precision required here. If the impactor had been traveling just 10% faster, both Earth and Theia would have been reduced to clouds of superheated vapor that never reassembled into solid planets. If it had been moving 10% slower, the collision would have been more like a cosmic fender bender with insufficient energy to melt and eject the massive amount of material needed to form our moon. Simulations indicate that only 1 to 3% of collisions between protoplanets produce large, stable moons. This means that even when all the mass, angle, velocity, and timing requirements are perfectly met, the chaotic nature of such violent impacts still results in failure 97 to 99% of the time. Most collisions either create multiple small moons that eventually crash back into the planet or scatter material so widely that it never coalesces into a moon at all. But the presence of the moon isn't just a matter of extraordinary luck. It plays a fundamental role in Earth's habitability that extends far beyond the dramatic story of its formation. Without our lunar companion, Earth would be a fundamentally different and far less hospitable world. Earth possesses an axial tilt. The angle between its rotation axis and the perpendicular to its orbital plane of 23.5 degrees. This tilt causes the seasons because different hemispheres receive more sunlight at different times of the year. When your hemisphere tilts toward the sun, you experience summer with longer days and more direct sunlight. When it tilts away, winter arrives with shorter days and the sun's rays striking at a more oblique angle. This seasonal cycle drives the fundamental rhythms of life on our planet. Plants and animals have evolved intricate biological clocks synchronized to these predictable changes. Migration patterns, breeding cycles, hibernation, and countless other behaviors depend on the reliable progression of seasons that our stable axial tilt provides. Without the Moon, Earth's axial tilt would vary chaotically between 0 and 85 degrees over timescales of millions of years. Imagine living on a world where the axial tilt randomly shifted every few million years. Sometimes the planet would spin upright like a top, with no seasons at all, and each region receiving constant amounts of sunlight year-round. Other times, it would roll on its side like a barrel, creating extreme seasonal variations where each hemisphere would experience decades of continuous daylight, followed by decades of perpetual darkness. During periods of extreme tilt, one hemisphere would bake under constant sunlight for decades, while the other froze in endless winter. Temperatures in the illuminated hemisphere could soar to over 200 degrees Fahrenheit, while the dark hemisphere plunged to -100 degrees or colder. No complex life could survive such dramatic swings between furnace-like heat and Arctic cold. Mars, lacking a large moon, experiences tilt variations between 15 and 35 degrees in periods of just millions of years. These oscillations cause extreme climate changes, alternating between severe ice ages and periods of intense warming. When Mars tilts more dramatically, its polar ice caps vaporize completely, creating brief periods when the atmosphere becomes denser and liquid water might temporarily flow on the surface. But these episodes don't last long enough for complex life to establish itself before conditions swing back to the other extreme. The Moon stabilizes Earth's axis through gravitational torque, a force that tends to rotate an object acting on Earth's equatorial bulge. This bulge results from Earth's rotation, making the equator about 13 miles more distant from the planet's center than the poles. Think of Earth as slightly flattened, like a basketball that someone is sitting on. The Moon's gravity acts like a cosmic gyroscope, preventing our planet from tumbling chaotically through space. With lunar stabilization, Earth's inclination varies only between 22.1 and 24.5 degrees in cycles of 41,000 years. These small and predictable variations allow relatively stable climates for hundreds of millions of years. The slight changes in tilt do affect Earth's climate. They're part of what drives the ice age cycles that have occurred over the past few million years. But these changes happen gradually enough that life can adapt. This stability is essential for the evolution of complex life, which requires millions of years to develop from simple organisms into sophisticated forms. Climate stability becomes even more critical when you consider the timescales involved in evolution. It took nearly 4 billion years for life on Earth to progress from the first simple cells to human civilization. If our planet's climate had been chaotic, swinging wildly between ice ages and greenhouse conditions every few million years, complex organisms would never have had the sustained periods of stability needed to evolve. The Moon also slows Earth's rotation through tidal friction over billions of years. When Earth first formed, a day lasted only 6 hours, not 24 hours as it does today. The planet spun like a whirling dervish, completing 4 rotations, while the sun moved just once across the sky. Imagine trying to live on a world where noon arrived every 3 hours and the sun raced across the sky at 4 times its current speed. The Moon transfers angular momentum, the quantity that measures an object's rotation, from Earth to its own orbit. This process continues today as the Moon gradually steals energy from Earth's rotation and uses it to slowly spiral outward. Each century, our days become about 2 milliseconds longer, and the Moon moves roughly 5 feet farther away. The effect is so gradual that you'll never notice it in your lifetime, but over geological time, it's been transformative. Without this deceleration, surface winds would be permanently catastrophic, exceeding 300 miles per hour. Imagine a world where hurricane-force winds never stopped blowing. The rapid rotation would create a Coriolis effect so intense that the atmosphere would be in constant violent motion. No complex life could survive on the surface of such a planet. Trees couldn't grow, rivers couldn't flow in stable channels, and the constant atmospheric turbulence would make the development of stable ecosystems impossible. The slowing of Earth's rotation also allowed for the development of complex weather patterns and ocean currents that help distribute heat around the planet. If Earth still spun every 6 hours, the atmospheric and oceanic circulation would be completely different, probably preventing the formation of stable climate zones that different species could adapt to over long periods. Moreover, the Moon generates ocean tides that may have been crucial for the origin of life itself. Tides create intertidal zones where fresh and salt water mix, concentrating organic compounds in pools that experience regular cycles of wetting and drying. These concentration zones may have provided the ideal environment for the first prebiotic chemical reactions. Picture the early Earth 4 billion years ago, with its moon much closer and tides hundreds of times more powerful than today. Vast tidal pools would have formed and evaporated in regular cycles, repeatedly concentrating organic molecules and providing the energy needed to drive chemical reactions that wouldn't occur in the open ocean. The rhythmic wet-dry cycles could have acted like a primitive laboratory, concentrating reactants and providing the energy gradients necessary for the formation of complex molecules. Statistically, only 1 in 100 planets in the habitable zone would develop a large moon through a similar impact. When you multiply this probability by all the other requirements we've discussed, the right type of star, the proper galactic location, the correct orbital characteristics, the presence of a protective gas giant, the numbers become staggering. Combining all the astronomical factors we've discussed so far, we arrive at approximately 1 in 1 million stars with the complete configuration necessary for complex life. But this number assumes that life arises automatically when suitable conditions exist, which hasn't been proven. Abiogenesis, the process by which life emerges from non-living matter, remains one of the greatest scientific mysteries. We still don't understand how the transition from chemistry to biology actually occurs. How did the first self-replicating molecules arise from the primordial soup of organic compounds? Experiments like the Miller-Urey experiment in 1952 demonstrated that organic molecules can form spontaneously under certain conditions. Stanley Miller and Harold Urey simulated the primitive atmosphere with methane, ammonia, hydrogen, and water vapor. After a week of applying electrical discharges to mimic lightning, they found amino acids, the building blocks of proteins, in their experimental apparatus. However, forming simple amino acids is enormously distant from creating the first self-replicating cell. The simplest known cell contains approximately 400 genes encoding proteins essential for survival. Each gene consists of hundreds to thousands of nucleotides, the chemical units that form DNA, arranged in specific sequences. The probability of a specific nucleotide sequence arising randomly is incomprehensibly small. To put this in perspective, imagine trying to write Shakespeare's complete works by randomly typing letters. The chance of getting even a single sentence correct would be astronomically small, and DNA sequences are far more complex and precise than any literary work. Some scientists estimate that abiogenesis might occur on only 1 in 10 planets with suitable conditions. This estimate assumes that favorable environments existed on the primitive Earth 4 billion years ago. Fossil evidence from structures called stromatolites, layered formations created by cyanobacteria, dates back 3.5 billion years, This suggests that life arose relatively quickly after Earth became habitable, within 500 million years. This speed could indicate that abiogenesis is more likely than we think, or we were extremely fortunate. The rapid emergence of life on Earth might suggest that given the right conditions, the chemistry to biology transition happens readily. But it could also mean we witnessed an extraordinarily unlikely event that occurred against astronomical odds. Assuming a conservative rate of 1 in 10, our accumulated probability drops to 1 in 10 million stars. But simple single-celled life isn't sufficient to create detectable technological civilizations. The journey from the first living cell to a species capable of building radio telescopes and space probes requires navigating through additional evolutionary bottlenecks that may be even more challenging than the origin of life itself. Bacteria dominated Earth for approximately 2 billion years before eukaryotic cells emerged. For half of life's entire history on our planet, nothing existed beyond simple bacterial mats and primitive, single-celled organisms. These bacteria were remarkably successful, developing photosynthesis, nitrogen fixation, and countless other biochemical innovations, but they remained fundamentally simple, lacking the internal complexity needed to build larger, more sophisticated organisms. Eukaryotic cells, cells with nuclei and complex organelles, are fundamentally different from simple bacteria. The transition from prokaryotes, cells without nuclei, to eukaryotes involved endosymbiosis, another extremely rare event. Endosymbiosis occurs when one cell engulfs another, but doesn't digest it, instead forming a permanent symbiotic relationship. Picture this extraordinary moment in Earth's history. A large bacterial cell somehow managed to engulf a smaller one, perhaps initially intending to consume it for food. But instead of digesting its prey, the larger cell allowed the smaller one to survive inside it. Over millions of years, this internal prisoner became an essential partner, eventually evolving into what we now call mitochondria. Mitochondria, the organelles that produce cellular energy, were originally independent bacteria 2 billion years ago. This fusion dramatically multiplied the energy available per cell, enabling vastly greater complexity. Before endosymbiosis, cells were limited by how much energy they could generate through simple chemical reactions. Afterward, they had access to efficient oxygen-burning powerhouses that could produce 20 times more energy. Think about what this means for the possibility of complex life elsewhere. Without this energy boost, cells remain forever trapped in bacterial simplicity. They can form mats, films, and simple colonies, but they cannot generate enough power to support the molecular machinery needed for complex internal structures, sophisticated sensory systems, or coordinated multicellular behavior. Evidence suggests that endosymbiosis may have occurred only once in Earth's entire history. Despite 2 billion years of bacterial evolution and countless trillions of individual bacteria, this crucial merger appears to have happened just once. Every complex cell on Earth today, from the neurons in your brain to the cells in tree leaves, descended from that single successful endosymbiotic event. If endosymbiosis is so rare, it might occur on only 1 in 100 planets where simple life already exists. This adds another devastating filter to our already slim odds. Even worlds that successfully develop bacterial life may remain forever stuck at that level, unable to make the leap to cellular complexity. After endosymbiosis, multicellular organisms, life forms composed of many cooperating cells, emerged 600 million years ago. Multicellularity evolved independently dozens of times, including animals, plants, fungi, and algae. This suggests that once you have complex eukaryotic cells, the step to multicellularity is relatively achievable. However, complex multicellularity with cellular specialization may be rare, perhaps occurring on only 1 in 10 planets with eukaryotes. There's a difference between simple multicellular organisms like algal mats and the sophisticated multicellular life we see around us. True complexity requires cells to specialize into different types: nerve cells, muscle cells, digestive cells, and coordinate their activities through elaborate signaling systems. Consider what had to happen for you to exist. Your body contains approximately 37 trillion cells, each one a descendant of that original eukaryotic fusion. These cells have specialized into hundreds of different types, from the rod and cone cells in your eyes that detect light to the cardiac muscle cells that keep your heart beating. They communicate through complex chemical signals, coordinate their activities with split-second timing, and somehow give rise to consciousness itself. Technological intelligence represents another potentially severe filter on the path to detectable civilizations. During 3.5 billion years of life on Earth, human-level intelligence arose only once. This single data point makes it extremely difficult to estimate how common intelligence might be elsewhere in the universe. Dinosaurs dominated for 165 million years without developing technology or complex language. These magnificent creatures ruled Earth for far longer than mammals have existed, yet none of them ever developed the ability to manipulate their environment technologically. Some dinosaur species were highly intelligent. Certain species of raptors may have been as smart as modern birds like crows or parrots, but intelligence alone isn't enough. Even after the extinction of dinosaurs 66 million years ago, mammals took 65 million years to produce humans. Think about that timeline. Mammals had the entire planet to themselves after the asteroid impact that ended the age of dinosaurs, yet it took nearly as long for human intelligence to emerge as dinosaurs had ruled before them. Large brains consume enormous amounts of energy. The human brain uses 20% of the body's energy, despite being only 2% of body mass. Your brain weighs about 3 pounds, yet it burns through roughly 400 calories per day just to keep running. This massive energy demand requires rich diets and environments that favor social cooperation and problem solving. The energy cost of intelligence creates a paradox. Big brains are expensive to build and maintain, so they only provide survival advantages under very specific circumstances. Most animals get along perfectly well with smaller brains that use far less energy. Elephants, dolphins, and great apes have large, sophisticated brains, but none of them develop technology. Intelligence also requires the right kind of body to be useful. Octopuses are remarkably intelligent, but they lack the long lifespans and social structures needed to accumulate and pass down technological knowledge. Their intelligence dies with each individual rather than building across generations. Technological intelligence specifically seems to require a combination of factors that rarely align. You need high intelligence, manipulative appendages like hands, social cooperation, long lifespans, and environments that reward tool use. Even then, the step from using simple tools to developing complex technology involves additional hurdles that most species never overcome. Conservative estimates suggest that technological intelligence emerges on only 1 in 1,000 planets with complex life. When you multiply all these independent filters, you obtain a combined probability that is catastrophically low. Taking 1 in 1 million for astronomical configuration, 1 in 10 for abiogenesis, 1 in 100 for eukaryotes, then 1 in 10 for multicellularity, and 1 in 1,000 for technological intelligence. The final probability approaches 1 in 100 billion, meaning perhaps only 1 to 4 civilizations in the entire Milky Way. Let that number sink in for a moment. In a galaxy containing between 200 and 400 billion stars, we might be talking about fewer civilizations than you have fingers on one hand. The vast majority of those stars shine on lifeless worlds, and even the tiny fraction that develop life likely remains stuck at bacterial or simple multicellular levels forever. And this calculation doesn't even consider the challenges civilizations face after developing advanced technology. We've assumed that any species reaching technological sophistication automatically becomes detectable and long-lasting. But what if that assumption is wrong? In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. During a conversation about flying saucers and aliens, Fermi asked a simple but profound question. Where is everybody? If intelligent life is common and stars have existed for billions of years, the galaxy should be teeming with detectable civilizations. Even traveling at a modest fraction of light speed, a single civilization could colonize the entire galaxy in 10 million years. 10 million years sounds like an eternity, but it represents only 0.07% of the Milky Way's age. The Milky Way is approximately 13.6 billion years old. Time enough for 1,000 complete attempts at galactic colonization. Yet we detect no artificial radio signals, no megastructures, no evidence of alien technology anywhere. This cosmic silence, the complete absence of detectable signals, constitutes Fermi's paradox. In 1998, economist Robin Hanson proposed the Great Filter theory to explain this paradox. The Great Filter represents a barrier or set of barriers so difficult that virtually no civilizations successfully traverse them. This filter could lie in the past, explaining why intelligent life is so rare that we appear isolated. Or it could lie in the future, meaning that technological civilizations systematically self-destruct or disappear before achieving interstellar prominence. If the filter lies in our past, we should celebrate. We've already overcome incredibly improbable stages. This would explain the cosmic silence without implying a dark fate for humanity. We would be the extraordinary exception that managed to navigate through all the evolutionary bottlenecks that trap most worlds in sterility or biological simplicity. Every step we've traced, from stellar formation to abiogenesis to endosymbiosis to intelligence, would represent another hurdle that virtually no other worlds have cleared. But if the filter lies in our future, the situation becomes existentially terrifying. It would mean that something ahead of us virtually guarantees the extinction or collapse of technological civilizations. In this scenario, we haven't beaten the odds yet. We're simply approaching the cosmic guillotine that has claimed every other intelligent species that ever arose in our galaxy. Nuclear warfare represents an obvious future filter. Humanity currently possesses an arsenal sufficient to destroy the biosphere multiple times over. It's estimated that 13,000 nuclear warheads exist today, with a total destructive power exceeding 5,000 megatons. 1 megaton equals the explosion of 1 million tons of TNT. The same energy as a magnitude 7 earthquake concentrated into a single, devastating instant. Imagine the power contained in our global nuclear arsenal. If you could somehow gather 1 million tons of TNT into a single pile, the explosion would be visible from space and felt hundreds of miles away. Now, multiply that by 5,000, and you begin to appreciate the destructive capacity humanity has created for itself. We've built enough weapons to turn every major city on Earth into a crater and poison the atmosphere with radioactive fallout for generations. Beyond direct destruction, nuclear winter. Atmospheric darkening from smoke and debris could last years or decades. Computer models suggest that a full-scale nuclear exchange would inject so much soot into the upper atmosphere that global temperatures could drop by 20 to 40 degrees Fahrenheit. Crops would fail worldwide, and the resulting famine could kill far more people than the nuclear explosions themselves. Anthropogenic climate change may constitute another filter, warming the planet beyond points of no return. Global average temperature has increased by 2 degrees Fahrenheit since the pre-industrial era, causing extreme weather events and ecosystem disruptions. Climate models project an additional increase of 3 to 8 degrees Fahrenheit by 2100, depending on future emissions. These numbers might sound modest until you consider what they represent. The difference between the current climate and the last ice age was only about 9 degrees Fahrenheit of global cooling. We are potentially approaching changes of similar magnitude in the warming direction, but happening in centuries rather than millennia. The last time Earth experienced temperatures significantly warmer than today, sea levels were 70 feet higher, and vast regions that currently support billions of people were uninhabitable deserts. Artificial intelligence represents a less obvious but potentially more devastating threat than our nuclear arsenal. Superintelligent AI systems. Artificial intelligence exceeding human capability in all domains could emerge within decades. Unlike nuclear weapons, which require deliberate human action to cause destruction, AI systems could pose existential risks through accident, misalignment, or unforeseen emergent behaviors. An AI system with goals misaligned with human welfare could alter the world in ways incompatible with human survival. Imagine an AI tasked with maximizing paperclip production that eventually converts all available matter, including humans, into paperclip-making machinery. This scenario sounds absurd, but it illustrates a fundamental problem: ensuring that extremely powerful optimization systems pursue goals that remain beneficial to humanity, even as their capabilities expand beyond human comprehension. The challenge becomes even more complex when you consider that superintelligent AI might be developed by multiple competing nations or organizations. Each group would face enormous pressure to deploy their systems quickly, potentially before adequate safety measures could be implemented. The first AI to achieve superintelligence might gain decisive advantages over all competitors, creating incentives for rush development that could prove catastrophic. Genetic engineering and biotechnology enable the creation of synthetic pathogens more lethal than natural viruses. Modern laboratory techniques could potentially create engineered diseases that combine the transmissibility of influenza with the lethality of Ebola, or design pathogens specifically targeting human immune systems or essential biological processes. Unlike nuclear weapons, biotechnology requires relatively modest resources and can be developed in ordinary laboratories. A determined individual or small group with sufficient knowledge could potentially create and release pathogens capable of causing global pandemics. As biotechnology becomes more accessible and powerful, this threat may become increasingly difficult to monitor or prevent. Technological acceleration means that intervals between disruptive innovations decrease exponentially. It took thousands of years to progress from agriculture to the Industrial Revolution, but only 250 years from steam engines to nuclear weapons. The time between major technological breakthroughs continues to compress, giving humanity less time to adapt to each new capability. This temporal compression may not provide sufficient time for civilizational wisdom to match technological power. Consider how rapidly we've progressed from the first controlled nuclear reaction in 1942 to building weapons capable of ending civilization. 75 years, barely a single human lifetime, separated the discovery of nuclear fission from the creation of arsenals that could destroy our species. The Great Filter suggests that a critical window exists between developing technology and acquiring the maturity to use it responsibly. Civilizations that traverse this window too rapidly may self-destruct before becoming multiplanetary species capable of surviving local catastrophes. The window might be narrowing as technological development accelerates, while human institutions, psychology, and wisdom evolve at their traditional glacial pace. Think about the coordination challenges we face as a species. We struggle to cooperate on relatively simple problems like managing fisheries or reducing pollution, yet we must somehow coordinate globally to manage technologies capable of altering the fundamental nature of intelligence, life, and matter itself. The mismatch between our evolved psychology and the scale of modern challenges may be inherently unsolvable. Observations of the universe show no evidence of civilizations that have overcome future filters. We detect no Dyson spheres, megastructures that would surround stars to capture all their energy output. Such constructions would be visible across interstellar distances as unmistakable signatures of advanced technological civilizations. The profound silence of the cosmos suggests that something systematically prevents civilizations from reaching detectable interstellar scales. Even civilizations that survived their early technological development should eventually become visible through their energy usage, communications, or large-scale engineering projects. The fact that we see none of this activity, despite billions of years for it to develop, strongly suggests that few, if any, civilizations successfully navigate whatever challenges lie ahead. Living in an extraordinarily rare solar system isn't cause for celebration, but for profound concern. If our system occurs in only 1 in 100 billion stars, this partially explains why we haven't encountered anyone else. But it also means that human waste and errors carry proportionally greater cosmic weight. We aren't just observers of the universe, we may be one of the very few examples of consciousness within it. The combination of suitable star, protective gas giant, stabilizing moon, and habitable planet is astonishingly improbable. Carl Sagan observed that we are made of stellar material, the universe becoming aware of itself through us. But if conditions for this self-awareness occur in fewer than 1 in a billion systems, our responsibility becomes immense. Every human decision about technology, climate, and survival may determine whether consciousness persists in this region of the cosmos. The atoms that compose your brain were forged in stellar cores billions of years ago, scattered through space by dying stars, and eventually assembled into a configuration capable of contemplating its own existence. You are, quite literally, the universe thinking about itself. But if we're correct about the extraordinary rarity of such systems, you might be among the only matter in this galaxy currently organized into conscious, reflective thought. The responsibility inherent in that realization should give every thoughtful person pause. The rarity of our system suggests that the great filter behind us was already extremely severe. This should bring relief. We've overcome astronomical odds simply to exist. Every breath you take, every thought you think, represents the culmination of billions of years of nearly impossible evolutionary achievements against staggering odds. But statistically, the more filters lie behind us, the greater the probability of catastrophic filters still ahead. If intelligent life were common, we would see evidence of it throughout the galaxy, through radio emissions and other technological signatures. The Search for Extraterrestrial Intelligence Project, SETI, has been monitoring the sky since 1960 without detecting any artificial signals. Vast radio telescopes like Arecibo, with its 1,000-foot diameter dish, and the square-kilometer array analyze trillions of frequencies across the electromagnetic spectrum. The square-kilometer array, when completed, will have a total collecting area of nearly 11 million square feet, 1,000 times more sensitive than current telescopes. This massive instrument will be capable of detecting signals from civilizations anywhere in our galaxy, assuming they're broadcasting with power levels comparable to our own television and radio transmissions. Yet the silence remains absolute. No transmissions, no artificial patterns, no signs of technology anywhere we look. This cosmic quiet is profoundly unsettling when you consider what it implies. If technological civilizations were even moderately common, the galaxy should be buzzing with their communications, their energy signatures, their inevitable expansion across star systems. This silence could mean that technology systematically destroys civilizations quickly before they become detectable. Perhaps there is something inherent in the development of advanced technology that leads to rapid self-destruction. Every civilization might follow a similar trajectory. They develop radio communications, nuclear weapons, artificial intelligence, and genetic engineering within a few centuries of each other, then quickly eliminate themselves before they can establish permanent settlements beyond their home worlds. Or perhaps advanced civilizations deliberately remain silent, fearing attention from other dangerous entities. This possibility leads us to what's called the dark forest hypothesis, which suggests the universe is like a forest where predators lurk in the darkness. In this analogy, announcing your presence is equivalent to shining a flashlight in a forest inhabited by unknown hunters. Maybe civilizations that survive learn to remain silent, explaining the absence of detectable signals. If the galaxy contains aggressive civilizations capable of destroying others, the safest strategy might be to develop advanced technology while maintaining absolute radio silence. Any civilization that broadcasts its location and capabilities might quickly find itself targeted for destruction by more powerful neighbors. Think about this chilling possibility. Every radio signal we've ever transmitted into space, from our earliest television broadcasts to deliberate messages like the Arecibo transmission, might be announcing our location to entities that view new civilizations as threats to be eliminated. Our naive assumption that contact with aliens would be beneficial might be catastrophically wrong. Alternatively, perhaps the universe is teeming with civilizations, but interstellar communication is technologically or economically impractical. The distances between stars present fundamental challenges that might be insurmountable even for advanced civilizations. Our nearest stellar neighbor, Proxima Centauri, lies 4.24 light-years away. 1 light-year equals approximately 5.9 trillion miles, the distance light travels in a year. To put this in perspective, if you could drive to Proxima Centauri at highway speeds, the journey would take more than 50 million years. Even at the speed of light, a round-trip message would take 8.5 years. The fastest spacecraft ever built, the Parker Solar Probe, reaches speeds of 120 miles per second at its fastest. At this velocity, it would take approximately 6,300 years to reach Proxima Centauri, making interstellar travel completely impractical with current technology. Even hypothetical fusion rockets or light sail propulsion systems would require centuries or millennia for one-way trips to nearby stars. Radio signals traveling at light speed would take years or decades to reach nearby stars. A bidirectional conversation with a civilization 100 light-years away would require 200 years to exchange a single message and response. This makes real-time communication impossible across interstellar distances, potentially explaining why the galaxy seems devoid of chatter, even if it contains numerous civilizations. These physical limitations might explain why the galaxy appears dead, even if life exists abundantly throughout it. Each civilization might be effectively isolated on its own world, unable to detect or communicate with others due to the vast gulfs of space and time that separate them. We might be surrounded by thousands of technological civilizations, all equally isolated and wondering if they're alone. But comforting explanations don't eliminate the darker possibility that future filters await us. Earth's history shows that mass extinctions have occurred 5 times in the past 500 million years, each one eliminating the majority of species alive at the time. The Permian extinction 252 million years ago eliminated 96% of marine species and 70% of terrestrial species. This extinction resulted from massive volcanism in Siberia that released greenhouse gases for millions of years, gradually cooking the planet until most life forms couldn't survive. The event was so severe that it's sometimes called the Great Dying. However, no previous extinction involved a conscious species capable of predicting and potentially preventing its own extinction. This capacity for foresight distinguishes us from every other species that has ever lived on Earth, but it also intensifies the moral weight of our collective decisions. We can see the asteroids coming, monitor volcanic activity, track climate change, and analyze the risks of our own technologies. Unlike the dinosaurs who had no warning of the asteroid that ended their reign, we have decades or centuries of advance notice for most existential threats. This knowledge gives us the power to act, but also the responsibility to choose wisely. Astronomy reveals that we occupy a position simultaneously central and peripheral in cosmic history. We're central because consciousness and understanding represent rare and precious emergences in the universe. The fact that matter can organize itself into configurations capable of contemplating existence and uncovering cosmic truths is extraordinary beyond measure. Yet we're also peripheral because our star, planet, and species occupy a mere temporary point in the vastness of space and time. The Sun will eventually exhaust its nuclear fuel and expand into a red giant, rendering Earth uninhabitable in about 5 billion years. Even our galaxy will eventually collide with Andromeda, potentially disrupting the orbital patterns that have kept our solar system stable. This duality presents a profound philosophical question about the meaning of human existence. If we're among the only conscious beings in a galaxy of hundreds of billions of stars, what does that say about our cosmic significance? Are we precious beyond measure because of our rarity, or ultimately insignificant because of our temporary nature? If we truly are one in billions, each individual human life carries a fraction of unique cosmic responsibility. You aren't just a person living on a planet. You're part of the universe's capacity to understand itself. The thoughts you think and the choices you make contribute to the cosmic total of consciousness and understanding. There is no known backup of human consciousness anywhere in the observable universe. The observable universe contains approximately 2 trillion galaxies, each with billions of stars, yet in the 100 billion stars of the Milky Way, there may be only 1 to 4 technological civilizations. In the galaxies beyond ours, separated by millions of light years, there's no possibility of contact or mutual support. The accelerating expansion of the universe, discovered in 1998, means that distant galaxies are moving away from us ever faster. Dark energy, the mysterious force causing this acceleration, comprises 68% of the universe's energy content. This expansion is gradually stretching space itself, carrying distant galaxies beyond our ability to see or reach them. Eventually, all galaxies beyond our local group will disappear beyond the cosmological observable horizon. In trillions of years, future observers in the Milky Way will see a universe containing only our immediate galactic neighbors, Andromeda, the large and small Magellanic Clouds, and a handful of smaller satellite galaxies. The vast cosmos that we can observe today will have expanded beyond visibility, leaving our descendants isolated in a small island of matter surrounded by empty, dark space. This growing cosmic loneliness makes it even more important to preserve consciousness wherever it exists. The rare solar system we inhabit resulted from an improbable chain of fortunate events. Each link in this chain, stable star, safe galactic location, protective gas giant, stabilizing moon, was necessary for complex life to develop and flourish. Remove any single element, and Earth would likely have remained sterile or life would never have progressed beyond bacteria. Without our G-type star's stability, the planet would have experienced lethal radiation bursts or frozen in premature stellar death. Without our suburban galactic location, cosmic radiation would have sterilized the surface repeatedly. Without Jupiter's gravitational shield, asteroid impacts would have prevented complex organisms from ever gaining a foothold. Without the Moon's stabilizing influence, chaotic climate swings would have made sustained evolution impossible. Picture Earth without any one of these factors. A world orbiting a red dwarf star would face constant radiation storms that strip away protective atmospheres. A planet in the galactic center would be bathed in deadly X-rays from the supermassive black hole and neighboring quasars. A system without a massive outer planet would suffer bombardment rates 1,000 times higher than Earth has experienced. A world without a large moon would tumble chaotically through space, experiencing climate variation so extreme that no complex ecosystem could persist. The statistical improbability of our existence doesn't diminish its reality, but rather increases its value. Existing against odds of 1 in billions confers an ethical responsibility not to squander this extraordinary opportunity. We are not just another species on another planet. We represent something unprecedented and perhaps unrepeatable in this region of the universe. Consider what this means for human civilization. Every war, every act of environmental destruction, every failure of international cooperation represents potential waste of cosmic significance. We're not merely damaging our own species or planet. We might be squandering the universe's only opportunity for self-awareness within thousands of light years. But responsibility shouldn't paralyze us with fear. It should inspire deliberate and careful action. Humanity has developed technology capable of altering Earth's biosphere on geological scales within mere centuries. This capacity transforms us from passive passengers to active pilots of planetary destiny. For the first time in Earth's history, a species possesses both the power to prevent natural catastrophes and the potential to cause artificial ones. We can track asteroids that might impact Earth and develop systems to deflect them. We can monitor supervolcano activity and potentially mitigate eruptions before they trigger global cooling. We can even begin to address the gradual brightening of the sun that will eventually boil away our oceans. No previous species in Earth's history had such capabilities. However, piloting requires wisdom proportional to power, and evidence suggests a dangerous lag between our technological capabilities and our collective judgment. Carbon dioxide emissions have reached 410 parts per million in our atmosphere, a level not seen for 3 million years. The pre-industrial concentration was 280 parts per million, representing a 46% increase in just 2 centuries. This increase drives global warming, ocean acidification, glacial melting, and increasingly frequent extreme weather events. Global average temperature has risen by 2 degrees Fahrenheit since the pre-industrial era, but this seemingly small change masks enormous consequences. Ice sheets in Greenland and Antarctica are losing mass at accelerating rates. Thermal expansion of seawater raises global sea levels, and changing weather patterns disrupt agricultural systems worldwide. The last time atmospheric carbon dioxide reached current levels, during the Pliocene epoch 3 million years ago, global temperatures were 5 to 9 degrees Fahrenheit, warmer, and sea levels were 50 to 80 feet higher. Most of Florida, the Netherlands, and Bangladesh would be underwater. Vast regions of Africa, Australia, and the southwestern United States would become uninhabitable deserts. But unlike hypothetical civilizations that failed before us, we possess scientific knowledge to predict consequences decades or centuries in advance. We can model climate systems, track atmospheric changes, and calculate the long-term effects of different emission scenarios with remarkable precision. Climate scientists have been warning about greenhouse warming since the 1880s, giving us more than a century to understand and address the problem. The capacity to predict doesn't guarantee the capacity to act, especially when action requires global coordination. The challenge of coordinating 8 billion humans with diverse interests may constitute a filter by itself. Game theory, the mathematical study of strategic decision-making, reveals fundamental collective action dilemmas that become more severe as the stakes increase. The prisoner's dilemma demonstrates how individually rational behavior can lead to collectively disastrous outcomes. In the classic scenario, 2 prisoners are better off if both cooperate, but each individual has incentives to defect regardless of what the other does. When scaled to global problems, this dynamic becomes extraordinarily dangerous. On a planetary scale, each nation might rationally prioritize economic growth over environmental sustainability. Developing countries argue they shouldn't sacrifice their economic development for climate goals when wealthy nations built their prosperity through carbon-intensive industrialization. Wealthy nations resist dramatic lifestyle changes that might reduce their economic competitiveness. Meanwhile, the climate system responds to total global emissions, not to the good intentions or relative virtue of individual countries. But if all nations act according to their narrow self-interest simultaneously, climate collapse harms everyone equally. This creates what economists call a tragedy of the commons on a planetary scale. The atmosphere is a shared resource that no single country owns or controls, yet every country's emissions affect everyone else's climate stability. Consider the mathematical structure of this problem. If cooperation provides benefits of 100 units to everyone, but costs 50 units to each participant, then mutual cooperation yields 50 units of net benefit per person. But if one country defects while others cooperate, the defector gains the full 100 units without paying costs, while cooperators lose 10 units each. This makes defection rationale for any individual actor, even though universal defection leaves everyone worse off than universal cooperation. Solving coordination dilemmas on a planetary scale has never been attempted before in human history. Previous civilizations faced local or regional challenges that could be addressed through traditional political mechanisms. Climate change, artificial intelligence development, nuclear weapons proliferation, and biotechnology risks all require unprecedented levels of international cooperation and coordination. The rarity of our solar system makes these challenges even more cosmically significant. If we fail, there's no evidence that another civilization in our galaxy is poised to emerge and continue the project of understanding the universe. The cosmos might continue for trillions of years without another opportunity for consciousness to arise in this region of space. This perspective should motivate both humility about our fragility and determination about our survival. We aren't inevitable or guaranteed. We are contingent, improbable, and potentially unique. The same cosmic lottery that produced us is extremely unlikely to produce another technological civilization within thousands of light years of Earth. This makes each human generation a temporary guardian of something irreplaceably precious. The knowledge we've accumulated about physics, chemistry, biology, and astronomy represents the universe's attempt to understand itself through us. The art, literature, music, and philosophy we've created constitute the cosmos exploring questions of meaning and beauty through conscious minds. When you look up at the night sky, you're not just observing distant stars, you're participating in the universe's capacity for self-reflection. The carbon in your brain, forged in stellar cores billions of years ago, has organized itself into patterns capable of contemplating the very stars that created it. This recursive loop of cosmic self-awareness may be extraordinarily rare. Great filter theory divides potential explanations for cosmic silence into specific categories. Past filters include abiogenesis, the transition to eukaryotes, multicellularity, and intelligence. Future filters include nuclear self-destruction, ecological collapse, misaligned artificial intelligence, and other existential risks that await technological civilizations. Bayesian analysis, a method of updating probabilities with new evidence, helps estimate where the most severe filters might be located. Each discovery of simple life elsewhere in the universe would suggest that early filters are less severe than we thought. This would shift probability mass toward future filters, making the outlook more threatening for humanity. This is why some scientists argue that not finding life on Mars would be better news than discovering it. Independent life on Mars would demonstrate that abiogenesis isn't an extremely severe filter, implying that future filters are more probable. Missions like Perseverance, which landed on Mars in 2021, actively search for signs of past life. The rover collects rock samples that will be returned to Earth in a future mission for detailed analysis in sophisticated terrestrial laboratories. The discovery of Martian fossils, or biomolecules, would fundamentally change our understanding of our cosmic position. If we found evidence that life arose independently on two planets in the same solar system, it would suggest that abiogenesis occurs readily wherever suitable conditions exist. This would be scientifically thrilling but existentially troubling, because it would shift the Great Filter firmly into our future. Jupiter's and Saturn's moons, especially Europa and Enceladus, may harbor subsurface oceans with life. Europa possesses an ice layer 49 to 82 feet thick, covering a global ocean with an estimated depth of 62 miles. This buried ocean contains more water than all of Earth's oceans combined, maintained in liquid form despite the Moon's distance from the Sun. Tidal heating, generated by gravitational flexing from Jupiter, keeps this ocean liquid despite the frigid conditions. Europa experiences constant gravitational kneading as it orbits Jupiter in an elliptical path. This flexing generates internal heat through friction, preventing the subsurface ocean from freezing solid. The same process that creates our ocean tides becomes a cosmic heating system capable of sustaining liquid water for billions of years. Enceladus, Saturn's moon with a diameter of 310 miles, ejects water geysers through cracks in its icy surface. These spectacular plumes shoot hundreds of miles into space, creating a temporary atmosphere around the small moon. The Cassini spacecraft detected complex organic molecules in these geysers during flybys between 2004 and 2017. Imagine what it would mean if life existed on multiple bodies within our solar system. If we discovered microorganisms in Martian rocks, living bacteria in Europa's ocean, and thriving ecosystems around Enceladus's hydrothermal vents, we would have to conclude that life is virtually inevitable wherever liquid water persists for extended periods. But the more common simple life becomes, the more alarming becomes the absence of advanced intelligent life. This would strengthen the argument that the Great Filter lies in the final stages, threatening technological civilizations just as they begin to reach for the stars. Consider the implications. If bacteria and simple organisms are common throughout the galaxy, but we see no evidence of technology anywhere, then something must systematically prevent simple life from evolving into spacefaring civilizations. Either intelligence is extraordinarily rare, or technological civilizations reliably destroy themselves before becoming detectable. This would make our current situation far more precarious than if we were simply rare from the beginning. Instead of being unlikely winners of a cosmic lottery, we would be walking a tightrope over an abyss that has claimed every other intelligent species that ever arose. Preparing for existential risks requires identifying the most probable threats and developing appropriate countermeasures. An existential risk is an event that would cause human extinction or the permanent and unrecoverable collapse of human civilization. This includes threats that would reduce humanity to small, isolated populations without the technological capacity to rebuild. The Center for Existential Risk at Cambridge University and the Future of Humanity Institute at Oxford University research these threats systematically. These academic institutions bring rigorous scientific analysis to questions that were once relegated to science fiction. They study everything from nuclear war and climate change to artificial intelligence and engineered pandemics. Mitigation strategies include space colonization, decentralized knowledge repositories, and improved global governance. Each approach addresses different categories of existential risk. Space colonization provides backup locations for human civilization. Knowledge preservation ensures that accumulated human understanding survives local catastrophes. Better governance helps coordinate responses to global challenges. Mars colonization could provide civilizational backup, ensuring that catastrophic events on Earth don't eliminate humanity entirely. Elon Musk and SpaceX are developing the Starship vehicle with the goal of transporting humans to Mars in the 2030 time frame. Starship has a planned cargo capacity of 220,000 pounds to Mars, sufficient to construct a permanent base. A self-sustaining Martian base requires local agriculture, water production, breathable air generation, and protection against radiation. The Martian atmosphere is 95% carbon dioxide with pressure only 0.6% of Earth's sea level pressure. This means that even with a pressure suit, a small puncture would be fatal within minutes as bodily fluids boil in the low-pressure environment. Radiation on Mars's surface reaches 200 millisieverts per year, 200 times higher than Earth's surface radiation. This level of exposure significantly increases cancer risks and could cause sterility, cataracts, and other health problems over extended periods. Martian colonists would need substantial shielding, probably requiring underground habitats or thick protective barriers made from local materials. Despite these challenges, establishing permanent human presence beyond Earth dramatically reduces the probability of total extinction. Even if Earth suffered complete nuclear devastation, runaway climate change, or asteroid impact, human civilization could continue on Mars and eventually return to restore Earth's biosphere. Beyond physical colonization, preserving human knowledge requires robust systems resistant to destruction. The Internet Archive stores 735 billion web pages and millions of books, films, and software programs. This represents humanity's largest repository of accumulated knowledge, but it remains vulnerable to local catastrophes affecting its data centers. The Svalbard Global Seed Vault in Norway preserves 1 million seed samples from around the world. This doomsday vault protects agricultural diversity against regional crop failures, climate change, and civilizational collapse. But even this impressive facility remains vulnerable to global catastrophes that might affect the entire planet. These initiatives protect against regional civilizational collapse, but remain vulnerable to global catastrophes. Ideally, copies of human knowledge would exist on the Moon, Mars, and other celestial bodies. A proposed lunar library would store synthetic DNA containing complete texts from terrestrial libraries. Synthetic DNA can preserve information for millions of years if protected from radiation in lunar caves. Unlike digital storage media that degrade within decades, properly stored DNA remains stable across geological timescales. the entire contents of the Library of Congress could be stored in a test tube weighing less than an ounce. Technologically, humanity possesses tools to mitigate many identifiable existential risks. We can track dangerous asteroids and develop deflection systems. We can monitor nuclear weapons and implement arms control agreements. We can research AI safety and establish international protocols for biotechnology. The technical challenges, while substantial, are not insurmountable. The real challenge lies in political coordination, collective will, and long-term planning horizons. Human political systems evolved to respond to immediate and tangible threats, not abstract and future ones. A politician who sacrifices economic growth today to prevent climate catastrophe 50 years from now faces immediate electoral consequences for distant theoretical benefits. This mismatch between evolutionary psychology and modern challenges may constitute a filter by itself. We're asking brains that evolved to handle tribal conflicts and immediate physical threats to coordinate globally on problems that unfold over decades or centuries. The cognitive and institutional frameworks that served us well for thousands of years may be inadequate for the challenges of technological civilization. Consider the temporal scales involved. Individual humans live for decades, political careers last for years, and election cycles occur every few years. But climate change, technological development, and existential risk mitigation require consistent policies maintained across multiple generations. Democratic systems struggle to implement policies whose benefits won't be realized until current voters and politicians are dead. Looking again at the night sky, our perspective has fundamentally changed after understanding our rarity. Each visible star isn't just a distant sun, but represents billions of years of stellar evolution. Most of these suns don't provide suitable conditions for complex life, for various reasons. Some burn too quickly, others suffer violent eruptions, and many orbit dangerous galactic regions. Red dwarf stars, which comprise 70% of all stars, produce lethal flares that would sterilize nearby planets. Massive blue giants burn out in millions of years, far too quickly for complex life to evolve. Binary star systems create chaotic gravitational environments where stable planetary orbits are impossible. Our Sun won the first cosmic lottery simply by being the right type of star in the right location at the right time. But that was only the beginning of an extraordinary chain of improbable events that culminated in your existence. Every breath you take represents the successful navigation of countless evolutionary bottlenecks that eliminated virtually every other potential path to consciousness. Some burn too quickly, others suffer violent eruptions, and many orbit dangerous galactic regions. Our star, the Sun, won the first cosmic lottery simply by existing in the proper category. But having a suitable star is only the beginning of the chain of necessary coincidences that had to align for your existence. Jupiter, often mentioned merely as a giant planet, functions as an essential civilizational shield. Without its presence in the exact orbit it occupies, Earth would be constantly bombarded by comets and asteroids. Every impact larger than 6 miles in diameter would cause mass extinction of dominant species. The asteroid that ended the dinosaurs was only about 6 miles across, yet it eliminated 75% of all species on Earth. Think about what this means for the continuity of complex life. Without Jupiter's gravitational protection, such devastating impacts would occur every few million years instead of every 100 million years. Complex ecosystems would never have time to recover and evolve sophisticated organisms before the next catastrophic bombardment reset the evolutionary clock. Picture Earth's history without Jupiter's shield. The Cambrian explosion, which gave rise to most major animal groups 540 million years ago, would have been cut short by asteroid impacts, just as life was beginning to experiment with complex body plans. The first fish would never have evolved into amphibians. Dinosaurs would never have ruled the Earth for 165 million years. Mammals would never have had the opportunity to diversify after the dinosaur extinction. Human evolution would never have begun. Each of these evolutionary milestones required millions of years of relatively stable conditions. The transition from water to land took 50 million years of gradual adaptation. The development of complex brains required tens of millions of years of selective pressure favoring intelligence. The evolution of social cooperation needed millions of years to develop the neural circuits necessary for language, culture, and technology. Without Jupiter's protection, none of these gradual processes could have completed before being interrupted by catastrophic impacts. Life would be trapped in an endless cycle of destruction and recovery, never advancing beyond simple forms that could rapidly repopulate after each bombardment. Complex organisms requiring millions of years to evolve would never have the uninterrupted time necessary for their development. The Moon, born from cataclysmic violence billions of years ago, continuously stabilizes our climate. Without it, seasons would vary chaotically, making the development of agriculture impossible. Earth's axial tilt would oscillate wildly between 0 and 85 degrees over periods of millions of years, creating climate chaos that would prevent stable ecosystems from ever establishing themselves. During periods of extreme tilt, one hemisphere would experience decades of continuous sunlight, while the other endured decades of perpetual darkness. Temperatures in the illuminated hemisphere could reach 200 degrees Fahrenheit, while the dark hemisphere plunged to minus 150 degrees Fahrenheit. Ocean currents would shift dramatically, weather patterns would become completely unpredictable, and ice ages would alternate with greenhouse periods on timescales too rapid for life to adapt. Sustainable agriculture emerged only 10,000 years ago, but it requires predictable climate patterns maintained across generations. This predictability enabled long-term planning, permanent settlements, and the accumulation of knowledge. Farmers needed to know when to plant and harvest, which required understanding seasonal cycles that remained consistent year after year, generation after generation. Without climate stability, human civilization could never have progressed beyond nomadic hunter-gatherer societies. The ability to store surplus food through predictable growing seasons allowed some people to specialize in activities other than food procurement. This specialization led to pottery, metallurgy, writing systems, mathematics, astronomy, and eventually all of modern technology. Human civilization, with all its complexity, fundamentally depends on this lunar climate stability. Every city you've ever visited exists because ancient farmers could predict when winter would arrive and plan accordingly. Every book you've ever read exists because scribes knew their crops would grow reliably each season, freeing them to pursue literacy. Every technological innovation that makes modern life possible traces back to the agricultural revolution that was only possible because the Moon keeps Earth's axial tilt stable within narrow bounds. Consider what happens on worlds without large moons. Mars provides a preview of Earth's fate without lunar stabilization. The red planet's axial tilt varies chaotically between 15 and 35 degrees every few million years, causing its polar ice caps to migrate from pole to pole. During high tilt periods, Mars experiences extreme seasons where one hemisphere faces decades of continuous sunlight, while the other endures decades of darkness and bitter cold. The complete combination, right star, right location, right gas giant, right moon, is astonishingly improbable. If we represented each factor as a die roll, we would be rolling a 10-sided die for stellar type, then a 100-sided die for galactic location, then a 1,000-sided die for gas giant configuration, then another thousand-sided die for moon formation and needing to get exactly the right number on each one. The probability of obtaining all the correct combinations approaches winning the lottery 100 times consecutively. Yet somehow against these impossible odds, every single requirement was met. Not just met, but met with remarkable precision. Earth orbits in almost the exact center of the habitable zone. Jupiter sits at precisely the right distance to protect without destroying. The Moon formed with exactly the right mass and orbital characteristics to provide stability. Think about the precision required for each element. If Jupiter were 20% closer to the Sun, it would have disrupted Earth's orbit during the solar system's formation, sending our planet careening into the outer solar system or spiraling into the Sun. If it were 50% farther away, it would provide no protection against comets from the outer solar system, leaving Earth exposed to bombardment rates 1,000 times higher than we actually experience. If the Moon were half its current size, Earth's axial tilt would still vary chaotically over millions of years, preventing stable climate patterns. If it were twice as large, tidal forces would be so extreme that they would prevent the development of complex life in coastal regions where many scientists believe life may have originated. But we won this cosmic lottery, and now we face the crucial question: what do we do with this prize? The Great Filter isn't an inevitable death sentence, but a statistical warning based on the observed cosmic silence. Every civilization that failed to traverse its filters probably had choices and opportunities, just as we do now. The difference is that we can see the filter approaching. Previous generations of humans faced threats they couldn't predict or understand. The Black Death struck medieval Europe without warning, killing 1/3 of the population before anyone understood disease transmission. The eruption of Mount Tambora in 1815 caused global climate anomalies that no one could explain at the time. Volcanic winter, crop failures, and famine seemed like random disasters rather than predictable consequences of natural processes. Humanity possesses a unique advantage: scientific knowledge to anticipate dangers before they materialize. Scientific prediction of climate change has given us decades of advance warning about rising temperatures, sea level rise, and extreme weather events. We understand the mechanisms of nuclear winter and can model its effects on global agriculture and civilization. We can analyze the risks of artificial intelligence development and biotechnology misuse before these technologies become uncontrollable. Previous generations didn't have this luxury, facing existential threats without understanding their causes or consequences. They couldn't predict volcanic eruptions, didn't understand disease transmission, and had no knowledge of asteroid impacts or climate systems. They lived in a world where catastrophes appeared without warning and departed without explanation, leaving survivors to rebuild without understanding what had happened or how to prevent recurrence. Our generation lives at a pivotal moment where present decisions determine whether humanity successfully traverses the Great Filter. There's no predetermined script, no inevitable destiny, only choices with measurable consequences. The decisions we make about technology development, international cooperation, environmental protection, and resource allocation will determine whether consciousness persists in this region of the universe. Consider the weight of this responsibility. Every vote you cast influences policy decisions about climate change, artificial intelligence regulation, and nuclear weapons control. Every consumer choice you make sends market signals about sustainable versus destructive technologies. Every conversation you have about existential risks contributes to humanity's collective awareness of the challenges we face. You're not just living your individual life. You're participating in the universe's attempt to preserve and expand consciousness. The carbon dioxide you emit by driving contributes to global climate change. The politicians you elect will make decisions about nuclear weapons policy and AI safety research. The companies you support with your purchases fund research that could lead to beneficial or dangerous technologies. Individual actions aggregate into collective outcomes that determine civilizational survival. 1 million individual decisions to ignore climate science produce collective inaction on emissions reduction. 1 million individual choices to support sustainable technologies create market demand for clean energy. 1 million conversations about existential risks build public awareness that enables political action. Living in a rare solar system isn't just a scientific curiosity, but a call to collective responsibility. We are temporary guardians of something potentially unique in this region of the galaxy, across billions of light years. This perspective should inspire not despair, but renewed determination to preserve and expand consciousness throughout the cosmos. The universe will remain vast and indifferent, but this indifference makes human choices cosmically significant. In a cosmos possibly empty of thinking minds, each human thought shines like a rare star in infinite darkness. Every moment of love, creativity, scientific discovery, or philosophical insight represents matter temporarily organized into patterns capable of experiencing beauty and meaning. When you feel overwhelmed by daily concerns, work deadlines, relationship problems, financial stress, remember that you are participating in something far grander. You are the universe becoming aware of itself, matter achieving consciousness, cosmic evolution reaching a point where it can contemplate its own existence and choose its future direction. The atoms in your body were forged in stellar cores that died billions of years ago. The calcium in your bones was created when massive stars exploded as supernovas scattered their contents across space and seeded the molecular clouds that eventually formed our solar system. The iron in your blood was synthesized in stellar furnaces hotter than 100 million degrees Fahrenheit. You are literally made of star stuff, and now that star stuff has organized itself into a configuration capable of understanding its own cosmic origins. Let's recapitulate the complete journey. We began with 300 billion stars in the Milky Way as our starting point. Of these, only 40 billion are G-type or K-type stars with sufficient stability, reducing our candidates to 1 in 10. Only 5% of these stable stars occupy safe galactic locations away from extreme radiation and dense spiral arms. This leaves us with 2 billion stars, but fewer than 1% have gas giants in the correct orbit to protect without destroying inner planets. Now we're down to 20 million systems, yet only 1 in 100 have large moons formed through the specific type of impact that created our moon. We've reduced our sample to 200,000 systems with complete astronomical configuration, less than 0.01% of the original stars. Applying the probability of abiogenesis at 1 in 10, eukaryotes at 1 in 100, multicellularity at 1 in 10, and intelligence at 1 in 1,000, we arrive at a combined biological filter of 1 in 100 million. Multiplying these biological factors with our astronomical requirements, we reach approximately 1 in 100 billion, meaning perhaps only 2 to 4 technological civilizations in the entire Milky Way of 300 billion stars. This calculation suggests that for every 100 billion stars, only a handful develop technological civilizations capable of radio communications and space travel. The fact that you're experiencing this moment right now represents the statistical convergence of billions of years of improbable interconnected coincidences. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.